Okay, welcome to the next part of your coordination compound. In this part, the second theory is EAN rule or effective atomic number rule. Effective atomic number rule, or it is also said to be Sedgwick theory. Sedgwick theory. Okay. Here the theory mentioned that if the total electron around central atom, total electron around central metal is equal to the highest noble gas configuration of that central metal is equal to the highest nearest noble gas configuration of central metal, then the complex will be stable. Or usually the complex have coordination compound where the central atom have, listen, in complex compounds, the central atom surrounded by electrons which equal to next nearest noble gas configuration or noble gas electrons. Okay, so usually how much electrons surrounded by central atom means it is exactly equal to the nearest noble gas electrons or nearest noble gas configuration. Okay, which means that is coordination compounds are stable if the total electron surrounded by central atom is equal to the nearest noble gas configuration. The coordination complex are stable. If it is not, then complex is unstable according to Sedgwick theory. Okay, so they may ask the question whether EAN rule valid or invalid. If it is valid, then the postulate is okay or the statement is okay, which means it will be equal to the nearest noble gas configuration. If it is not valid, there may be a variation. Okay, so that is coordination compounds. Listen, coordination compounds, that is coordination compounds satisfying EAN will be stable according to the theory. Okay, then how can you find the electrons around central atom? First of all, you have to consider the atomic number of central atom, and moreover you have to consider the oxidation state. If the oxidation state is +3, which means 3 electrons are dropped from the atom comparing to its neutral form. Okay, if my atomic number is 26 but I am existing in a +3 oxidation state, then what is the electron surrounding me is not 26. My atomic number is 26 and I am existing in a +3 oxidation state, then the number of electrons surrounded by me is not 26. It is actually 26 dropped by 3 electron or dropping of 3 electron. Consider the drop of 3 electron, then 26 minus 3, that's equal 23. So my electron is 23. So that is the electrons surrounded by central atom. That is moreover, one more thing is, if I surrounded by 10 ligands, and each ligand surrounded by the central atom by means of 2 electrons. So 10 ligands, which also produces 20 electrons. Okay, so in addition to 23 electrons by metal, the electrons surrounded by ligand also we have to consider. Okay, so a coordinate bond have 2 electrons. Okay, so what is the total number of coordinate bonds in an atom or in a central atom? It is equal to coordination number. So how much electrons surrounded by ligands around a central atom means it is the double of the coordination number. Okay, so you can find the sum of total electrons around metal plus the electrons contributed by the ligands. Okay, so to find the EAN effective atomic number, you find the atomic number of metal, atomic number of central metal, atomic number of central metal. Then minus the oxidation state, Minus the oxidation state means if the oxidation state is plus 3, then you have to minus 3 electrons. So minus the oxidation state. Atomic number of metal minus the oxidation state plus 2 into coordination number. Coordination number means number of coordinate bonds around central atom, and twice that you obtain the electrons. So this is a case. Okay. So let me check this in the compound hexamine cobalt 3. So this is a compound hexamine cobalt 3. Hexamine cobalt 3. Ready? Fine. So what is the atomic number of cobalt? Cobalt having atomic number of iron, cobalt 27. 27 means actually 27 electrons are there. What about the oxidation state of cobalt here? Cobalt, the total entity have plus 3, ammonia have 0, so this will be plus 3. So oxidation state, atomic number is 27. So your EAN is equal to, atomic number is 27 minus the oxidation state is 3 plus, what about the coordination number? Coordination number, the ligands are amines. So 1 into 6, coordination number is 6. So 2 into 6. So this is 24 plus 12. And that's equal to 36. Perfect. 36 is the atomic number of the highest noble gas or nearest noble gas, krypton. So here EAN valid. EAN rule valid. Okay. But it is not actually valid in all cases. Let's consider the next example. If I have FeCN 6 times 3 minus. What about the atomic number of Fe? Fe having an atomic number of 26. What about the oxidation state here? Oxidation state minus 3 and cyanide, 6 cyanide of minus 6. So this will be plus 3. So oxidation state is plus 3. What about the coordination number? The ligands are monodentate ligand cyanide with the 6 numbers, so 6. So EAN, let's consider the EAN. EAN is equal to, tell me. OS is equal to, EAN is equal to, fine. Atomic number 26 minus 3 plus 2 into 12. I'm sorry, 2 into 6. So that's equal to 23 plus 12. That's equal to 35. So EAN not valid here. EAN is not valid. And you know, this molecule is said to be hexacyanoferrate. This is ferric. Hexacyanoferrate 3. Okay. Now the next, FeCN 6 times of 2 minus. Fe atomic number 26. Oxidation state here is minus 6. So this will be plus 2. So oxidation state of iron is plus 2. And coordination number, once again the 6 ligands, 6 into 1. So EAN is equal to 26 minus 2 plus 2 into 6. So that's equal to 24 plus 12. Fine, perfect. So that's equal to 36. 36 is the configuration of krypton. So this is perfect. Ferric cyanide. Ferrocyanide is okay. Or hexacyanoferrate 2 is okay. But ferrite 3 not satisfying the EAN rule. Okay? Clear? Okay. So now we can check the validity of EAN rule in some more examples. Okay? Check the validity of EAN rule in some more examples. Ready? Write a question. Check EAN rule in the following. Check EAN rule in the following. Okay. Your first example. AuCl2 minus. AuCl2 minus, where the atomic number of gold is 79. Oxidation state -1, chlorine half -2, chlorine half -2, so this will be +1. Oxidation state +1. Coordination number 2 into 1 equal to, okay, so En 79 minus 1 plus 2 into 2, 78 plus 4, that's equal to 82. So 82 is not a configuration of noble gas. You know the configuration of noble gas, electrons of noble gas, 2, 10, 18, 36, 54, 86, like that. Okay, so here AN rule is not valid. Next example, FeC2O4 thrice 3 minus. Okay, Fe26, ready? Oxidation state is this of 3 minus, and this you know, -2 into 3, oxalato -6, so this will be +3. So oxidation state +3. Coordination number density 2, number of ligand 3, 6. So En is equal to 26 minus 3 plus 2 into 6, and that's equal 23 plus 12, that's equal 35. Not valid. Okay, next, Ca EDTA -2 minus. Okay, ready? Ca EDTA 2 minus. Fine. Now calcium with atomic number 20, oxidation state, EDTA have 4 minus charge, so calcium will be +2. Calcium always +2, you know, and coordination number is equal to, if the charge of EDTA is -4, then the coordination number is density is 6, so coordination number is equal to 6. Okay, so coordination number is 6. Ready? If the coordination number is 6, what happened? Listen. En is equal to 20 minus 2 plus 2 into 6, that's equal 18 plus 12, that's equal 30. So En not valid. Ready? En is not valid here. Okay, so the next example, Ni NH3 thrice En Py all of +2. Nickel with atomic number iron, cobalt, nickel, copper, zinc. So nickel with atomic number 28. Oxidation state, you know, pyridine have 0 charge, ethylene diamine have 0 charge, ammonia have 0 charge, so nickel is in +2. And coordination number, amines 3, density 1, ethylene diamine 1, density 2, pyridine 1, density 1, 3 plus 2 plus 1, fine, 6. So En is equal to 28 minus 2 plus 2 into 6, so that's equal to 12. En not valid. En not valid. Ready? Okay, fine. So these are the cases. Okay, one more question I'll give you. So most of the case where En rule is not valid, right? Okay. One more case. So you, I think you are familiar how to find, how to calculate the EAN, right? Find N for stable, find N for stable carbonyls, stable metal carbonyls. According to EAN rule. For example, you have FeCO n times and you should find the N. So what is the nearest noble gas of followed by iron means? Iron have atomic number of 26. So nearest noble gas means krypton of 36. So this have to follow what? The electron of krypton, right? Okay, the total electron here will be krypton, then only this become stable. Then for that, how much N is required? That is the case. Here the oxidation state is 0. Because all charge is 0, carbonyl have 0 charge, so ion will be in 0. So coordination number, we know that carbonyl is monodendrite, but the N number is N. Now let's check what is N. We know NEN is atomic number minus the charge plus 2 into coordination number. For a stable molecule, this value will be equal to the nearest noble gas configuration. Nearest noble gas is krypton. So this En will be equal to 36. Okay. So 26 plus 2n is equal to 36. Ready? If you are cutting this one, here will be 10. So 2n is equal to 10, which implies that n is equal to 5. So question like this may also ask using EAN rule. Okay, so that's all about EAN rule. Most of compounds which do not satisfy the EAN rule. Okay, so EAN rule is not a condition for formation of coordination bond or a stability criteria, and that is clear. Ready? So we are moving to the next theory, that is your valence bond theory. So the next theory, that is valence bond theory. Number 3, third theory, we already know that from your chemical bonding, valence bond theory. Okay. So what about the valence bond theory means? Valence bond theory states that as your same as in the covalent bonding, here the central metal atom, where the orbitals of central metal atom, vacant orbitals of central metal atom undergoes hybridization to form a set of similar orbital with the similar empty hybrid orbitals. To that, your ligand donates 2 electrons or forms a coordinate bond. Okay, so here vacant atomic orbital of, you know the concept of hybridization, we already discussed it from chemical bonding. Okay, so vacant atomic orbital of central atom, it's not halfly filled, it is vacant. Vacant atomic orbital of central atom undergoes hybridization to form new hybrid orbitals. Okay, usually or simply, the vacant hybrid orbital, to that vacant hybrid orbitals your ligands donate, or your ligands forms the coordinate bond. The vacant hybrid orbital filled by donating 2 electrons from ligand, to form the coordinate bond. Okay, central metal can use either ns, np or n-1d orbital for hybridization, and that is said to be inner orbital complex. And molecule were n-1d orbital used, then it is said to be inner orbital complex. That coordination compound is said to be inner orbital complex. Okay. I'm sorry. Or they can use, can use NS, NP or ND orbitals for hybridization. NS, NP or ND orbital for hybridization. And that is said to be outer orbital complex. Okay. Use of ND and n-1d orbitals depends on ligand field strength. Ligand field strength. What the ligand field strength is actually obtained from spectrochemical series. What the spectrochemical series is discussed in coordination compounds. Okay. Simply, what is a ligand strength means? The ligand strength is like this. The ligand strength is CnOx. This is a simple order of ligand strength. CnOx. Okay. Ligand field strength. So halogens have relatively weak field strength than oxygen, then nitrogen, then carbon. So carbon have greater field strength. Ready? Fine. So usually if a strong ligands are happening, or if a strong ligands occurring, in case of occurrence of strong ligand usually n-1d orbitals are used. Okay, in case of strong ligands, n-1d orbitals used. Ready? And generally diamagnetic. Generally, strong ligands paired the electrons. Paired the electrons to inner orbital. Paired the electrons to inner orbital. I'll explain this using example, then only it will be clear. Okay, so pair the electron to inner orbital. Okay, usually the strong ligands which can pair the electron to inner orbital. If it pairs the electron to inner orbital, what is a speciality means? Generally, it's not in all case, generally it may be diamagnetic. Okay, and in case of weak ligands usually using the orbital of ND if it needs. Ready? And generally weak ligand not able to pair the electron. Okay, so it is not always. Generally, since the electrons are not paired, it may be free. If it may be free, there will be free unpaired electron. So molecule, generally it is paramaterial. That's a general statement, not in all case. Okay. Generally, if the hybridization is sp, then the shape is linear. Here, if the hybridization sp2, then the shape is trigonal planar. Okay. For sp hybridization, coordination number will be 2. For sp3 hybridization, coordination number will be 3. If the hybridization sp3 tetrahedral, well, the coordination number is 4. One more hybridization in coordination number 4 in case of strong ligands, that is dsp2, using in the inner d orbital. Well, the shape is square planar. Shape is square planar actually, and the coordination number is 4, remains the same 4. Okay, and in case of coordination number 5, it is either sp3d or in case of strong ligands, there is dsp3. dsp3 means inner d orbital, sp3d means outer d orbital. Okay. Both have same shape, trigonal bipyramidal. Trigonal bipyramidal. And both have same coordination number 5. And one more is usually the sp3d2, the most important or the most common one, or d2 sp3. Both have coordination number 6 and the geometry very same. In both the geometry is octahedral, where the coordination number is 6. Okay, so that's all about the valence bond theory postulates. So valence bond theory actually introduced by Pauling, but the concept is here hybridization. Okay, so hybridization represents that the here central metal with the vacant d orbital undergoes, or vacant orbitals, not d orbital, vacant orbital undergoes hybridization. Ready? To form set of new vacant hybrid orbitals. To that hybrid orbitals, electrons can form coordinate bond. Ligands can form the coordinate bond. Okay, and the central atom may use outer d orbital or inner d orbital. That depends on the ligand field strength. Okay, but the ligand field strength is greater for carbon, then nitrogen, then oxygen, then halogen. That's a general idea. We will clearly write the ligand field strength based on crystal field theory using the spectrochemical series. Okay, so the rough idea is carbon, nitrogen, oxygen, halogen. That is a decreasing order of ligand field strength. If in case of strong ligands, the strong ligands can pair the unpaired electron to paired one, so that it may be diamagnetic, or the inner d orbitals may be vacant. So it can use the inner d orbital to form the inner orbital complex. Or in case of weak ligands, they try to bring the ND or outer d orbitals for hybridization. Okay, they won't take much risk like strong ligand. So usually, if there are any unpaired electron in the inner orbital, they exist still as unpaired electrons. So the molecule will be paramagnetic. Ready? So these are the cases. Okay, and forms since it used outer d orbital, it will be outer orbital complex like that. And depends on the coordination number, the hybridization possibilities may be different. If the coordination number is 2, hybridization may be sp. It is rarely seen in your case. Okay, usually it is coordination number 4 and coordination number 6 are usually we can see in this chapter. Okay, so we'll discuss that. So let's have a discussion about the hybridization of some examples where we want to find the magnetic property, whether it is paramantic or diamantic like that. And also we want to find the we want to predict the hybridization of molecules. Ready? Fine. And to find the magnetic moment, what about the case? To find the magnetic moment, the formula is root of n into n plus 2. Okay, to find the magnetic moment, the formula is root of n into n plus 1. For the unit is Bohr magneton. Sometimes the magnetic moment also asked in question where n is the unpaired electron. You know that. Where n is the unpaired electrons. Okay, fine. So we can discuss it in some examples. Ready?